So, we are going to continue looking at hierarchical reinforcement learning today, and so what we saw in the last class was essentially a very long drawn motivation for why you want to do hierarchies, right, and then I spoke about a lot of issues that might creep up, right. So, it is more at a very intuitive level, right, and finally towards the end of the lecture we actually looked at SMDPs, right. So, which is a model that many of the hierarchical learning architectures use as the underlying mathematical formalism. Okay. So, what we will do today is start looking at some of those hierarchical frameworks. Okay. The first one we look at is called the options framework. So, chronologically it is not the earliest, but in some sense it is the simplest of the hierarchical frameworks, and therefore we will start there. So, the basic idea behind options is something very simple. So, I am going to take the solutions to these sub problems that we are defining, right. So, I just take the solutions to those, right, I will encapsulate them as a single action. So, the idea comes from the planning literature actually, where people talk about something called macro actions. Right. So, in the planning community, macro actions are essentially just a sequence of actions put together, and then you talk about it as a single action, right. So, for example, I mean we spoke about many such examples in the last class, right, and so want to get down the go out of this building, I can have a macro action that says climb down the stairs, right, that consists of a lot of smaller actions, but then as far as I am concerned all I need to think of it is as a single action that says climb down the stairs, right. So, and in the planning literature you just have a sequence of actions, right, but then when we move to the reinforcement learning space, there is something else that we need to take care of. What is that? I can't just blindly specify a sequence of actions. Let us take the go down the stairs case. Can I just say, okay, stand at the top of the stairs, okay, then put your right foot out down once, put your left foot down once, and keep doing this, I don't know, 120 times, and you will reach the ground floor, right. So, can I specify a macro action like that? What could go wrong? Huh? Whatever, okay, let us assume that I get the floor right. Is there anything else that can go wrong? Huh?
Balance.
Let us assume I get the balance right.
So, directions can go wrong.
Let us assume I get the direction right. But when can the direction go wrong?
Yeah, you don't know whether the steps have same direction.
Yeah, I am assuming I have learnt all of that.
Okay.
People could just be coming up the stairs, right? I might have to stop, move to the side, let them out. I can't just keep bulldozing.
Huh? All that is already learned.
No, these are things that are dynamic, right? See, the direction of the stairs turns and all those things are static. So I could plan for all of that and then say, okay, this is the direction in which I will be taking my steps and so on and so forth, right? So all of that I could plan for, but then there are other dynamic components to the world, right? And suppose there is some kind of slipperiness associated with the stairs, right. So, I keep going down and then suddenly some stair I could skid and then I might actually fall down a few steps, I mean not really fall down, but then like skip ahead a few steps, right, or suddenly there could be I don't know, this happens in the other day it happened to me when I was climbing down the civil engineering department. Suddenly there is this one step there where there is this big chunk of concrete taken out of the step, right. I was talking to somebody and then I was actually holding a cup of coffee in my hand, I was walking, suddenly there is no step there, okay. I just skipped the step and actually had to step on the next step. It kind of puts a stride off, right, and then I had to actually go down a few more steps very quickly to regain my balance. So, these kinds of things happen, right, these are all dynamic things, you do not know. small changes that are happening and so on and so forth. We are actually all this while when we are talking about solving the reinforcement learning problem, we have been assuming we live in a stochastic world, right. So things can go wrong, right. So what do you need to specify to get a macro action right? Not a sequence of actions, but start and an end, but I need a solution to the problem, right? Huh? Close.
Observations.
Right. So what you need to specify is a policy, right. So an option is essentially some kind of a, I am going to call it some kind of an encapsulated policy, okay. Great. So now let us go back to the example I was actually giving you already. So how did I describe this macro action for getting downstairs? Huh? How did I start the description?
Stand in front of the steps.
I said stand in front of the steps, right. So I need to be able to tell you where these macro actions are applicable, right. I need to tell you where they are applicable. I can't just say okay get down the stairs now, right. So if I say get down the stairs here, I mean that really it won't work, right. So I have to be actually there. This is not a new idea. Even for simple actions I need to be able to specify where the action is valid, right. So I can't just say, you know, playing chess the first move can't be capture the king, right. So I have to set it up that there has to be a mate condition before I can say go cut the king, right. So those kinds of things. So I need to tell you where to start and then I need to tell you where to end, right. If I exactly I was telling you do this 130 times and then you will end at the ground floor, right. So I need to tell you where to end. So I put all of these things together. So if I want to specify a useful macro action, so I need something that tells me where the initiation can happen, right. Then I need a policy to use while the macro action is executing, and then I need a termination. Okay.
So those two, then initiation and termination, can we stage within that particular encapsulation?
Sorry?
Initiation and termination,
Yeah.
we just start and end stage within that particular encapsulation.
It can be start and end states, I agree, but why? What do you mean by within the particular encapsulation? The encapsulation is just a policy, right? Just a policy. So I assume that wherever I can start the policy, I will have some action defined for that policy, right? So let's say talk about that a little further as we go along, right? So the initiation, if you look at the classical options framework, right? I mean it's proposed in 99. I propose we can suppose we can start calling it classical now. If you look at the classical options framework, they usually give this as a set of states, right. So initiation set denoted by I is a subset of the state space, okay, and then the policy is given as if it is a deterministic policy it could be this, right, or it could also be given as a mapping of or it could also be given as a mapping of history. I will elaborate a little bit more, but it can be given as a mapping of a history of things that have happened since I started doing this to the next action, right. So that allows us to define options like okay, go 3 steps forward and then turn right. It might be useful, right. So what happened there when I said go 3 steps forward and turn right? Automatically added history to the policy. So I need to count, okay, what was my last action? Was it go forward? Okay, what was the last 2 actions where they both go forward? What are the last 3 actions where they both they all three go forward, right, and then if that is the case, then I do a write action, right. So I could define it like that. I will come back to that. And the termination is typically specified by beta, right, is in the original definition of the option is given by a probability. So beta of S will be the probability that that option will stop in state S, right. So for many states the probability could be 1, because that means on all those states the option, if you reach that state, the option will not continue.
In RL we started as you never specify the goal to the agent.
Is it?
In RL we started as we never specify the goal to the agent, but you are specifying a termination point to the agent.
Yeah, but this is not the RL problem I am solving, right?
This is planning.
Huh? No, it is just an action I am defining, it is not a problem. So suppose you say, you can't tell me that, oh, in the agent if it goes north, you shouldn't say that it's actually move up one step, right? I mean, that's the dynamics of the problem. I'm just defining the dynamics here, right? So these are the three components that make up an option, right? So for a particular option, I can probably add a vote everything. So I have the basic MDP, which is some states, actions, and so on and so forth, and an option is going to consist of these three things. Okay. So this probabilistic definition of options was actually introduced for more of a mathematical convenience, right? So that they could show some proofs more elegantly. In practice, when you define these options, you typically make the probability of termination 0 or 1. So 0 means it does not terminate, 1 means it terminates, right? So you can think of it as an indicator function, that it indicates whether the set belongs to the termination set or not. Right. So you could think of the initiation and the termination being sets. Okay. Right. So there are two kinds of options, right? So which I'll Markov options, which are easy enough to define. So what are Markov options? Huh? Sorry? Yeah, exactly. So pi naught is defined only on the current state, right? So these are Markov options. So the nice thing about Markov options is I don't have to worry about where I started the option, right? So wherever it is, it will be the same action, right? So if I am in a particular state and I am executing that option, then I will take the same action. Okay. Okay. In the second class of options called semi-Markov options. So what are semi-Markov options? Why is semi-Markov? Why not non-Markov?
Sequence of states since the option.
Sequence of states since the option was initiated. Right? If you remember, I was telling you why is a semi-Markov, because during the execution of the option there is a dependence on history, or could be a dependence on history, we do not know, right. So I was telling you when the holding time is in operation, you really do not know how the system is behaving. So and I said that is the reason we are calling it semi-Markov. So in a semi-Markov option, so pi naught depends on Why not depends on history since the option started. So let us say I have a if I start here, right, and say go right 2 steps and down 1 step, right. So it will be this, right, 1, 2, and then this, right. So in this state I go right, in this state I go down, right. But if I started the option here and said go right 2 steps and one down 1 step, right, it will be this, and then that, right. So what I do in this state depends on where I started the option, right. Whether I go right here or whether I go down here depends on where I started the option. If it had been a Markov option, right, it shouldn't matter where I start the option. When I come to this state I should be taking the same action.
Can you give an example where this would be helpful and non-Markov? I mean, a Markov would not be very helpful, but this one.
So there are many instances where we want to allow your agent just to do a larger amount of exploration. Okay. So if you are, how many of you have finished all your programming homeworks? Q learning, right. If you think of how hard it would be if you make the puddle world 10,000 by 10,000 puddle world. Did people try it? Isn't it part of the assignment? What is part of the assignment then?
It's 12 by 12.
12. We didn't give them a functional approximation assignment at all?
Yeah, there is also one that.
On the 12 by 12? What's the fun in that? When did you change the problem statement? I thought I gave 1000 by 1000. At least 1000 by 1000. 12 by 12 there is no fun. Why do you even want to do functional approximation on a 12 by 12 grid world? At least 1000 by 1000 grid world.
But how will they show the policy?
Huh?
It will be too large to even show.
What's that?
You need to show, like, you need to submit the policy.
That's a fun. That is the fun part. What do you mean by store the policy? Why do they need to store the policy? They just need the Q function, right?
No, not so. They need to turn it in. They need to, the report you need to submit. What you
That's bookkeeping. I don't care. I mean, you just ask them to plot learning curves, right? That should be good enough for the function approximation case. They shouldn't ask them to turn in the policy.
how are we going to like encode the world in that case?
Huh?
It will manually note down where to put it.
Your computer is a very smart computer science case. Can't you figure out how to do that automatically? Right? I mean, just look at it, blow up the puddle and figure out rules for where the puddle should be, right? And then write a small function that initiates the puddle world. That's easy enough to do. Don't tell me you can't do that. Right? Anyway, how long would Q learning take to work in a 1000 by 1000 grid world or a 10,000 by 10,000 grid world? You saw how long it takes, right? I mean, it takes, even in a 12 by 12 grid world, it just takes a while to do all the exploration and so on and so forth. In situations like that, you really want your agent to have the ability to do crazy things in one shot, right? So, for example, imagine a 1000 by 1000 grid world where I define an option that says go in this specific direction for 15 steps. So I can just go north 15 steps, or go east 15 steps. See, in the puddle world, it is not really clear to me what are useful options to begin with, right? I mean, what are useful options? There are no doorways. What are useful options in the puddle world?
Puddle is kind of repeating.
Huh?
The word is there is
If the puddle repeats, but the kind of a puddle world I gave in the RL, that one big puddle in the middle of the world. There really no bottlenecks or anything that, I mean, there are bottlenecks, but it's not immediately obvious to you what the bottlenecks are. So the bottlenecks would be the edge of the puddle before it ends. So essentially you have the puddle like this, right? Right, and then there is a goal here and the start state here. Right, this would actually be a bottleneck if you think about it. Right, so this could be a bottleneck. So you need to get there before you can actually get to the goal. Okay, so those states will act like bottlenecks. Right, so but then that's not useful, really that interesting an option, right? So what you could do is just define or what the goal was here, is it? Wherever you kind of can guess where the option bottlenecks would be, right? So you can kind of define options that essentially make it more efficient to explore by saying that go up 15 steps, right, or go right 15 steps, right? So that way, whenever you pick this action by accident, when do you pick it by accident? When you are doing exploration, right? Your epsilon greedy thing. When you go up by 15 state, suddenly you break out of your random walk loop, right? So you move away 15 steps and then you start doing a random walk there, right? And then you take another action, then you will move away another 15 steps and you will start doing a random walk there. That way you essentially can explore a lot more of the state space than you can if you are just working with primitive actions. So in such cases, having this kinds of options are helpful.